guys, welcome back to our channel. This is George Kamiti. The question of today, we are still dealing with simple stresses and strains, and we got this question that we need to solve. A steel rod that is shown in the figure below is have got 50 millimeters diameter and it is 2.5 meters long. And the cross section, this circle shows that the cross section of this steel rod is circle. It is subjected to a pull or a tensile force of 100 kilonewtons. And the question is, to what length should the rod be bored centrally so that the total extension will increase by 15% under the same pull of 100 kilonewtons? And the diameter of the bow that is to be bored is 25 millimeters in diameter. Take Young's modulus of elasticity of steel to be 200 giganewtons per square meter. So this diagram, the first diagram here is showing the complete steel rod with a diameter of 50 millimeters and a length of 2.5 meters, subjected to tensile force of 100 kilonewtons. This steel rod should be bored centrally, so we need to know up to what length should it be bored, so that when the bored rod is subjected to a force of 100 kilonewtons, the extension increases by 15%. That is, the extension of the solid rod increases by 15% after it has been bored. So that is what we are supposed to determine. So join me so that we do this. Now, we are going to begin with calculating the stress of the solid steel rod. We calculate its change in length. Now, we know that the Young's modulus of elasticity is given by the ratio of stress to that of strain. Stress is given by load divided by cross-sectional area, and strain is given by change in length divided by the original length. So when we substitute this formula to this stress, we are going to get load over area divided by strain, which is change in length divided by the original length, which is going to give us load times length divided by cross-sectional area times the change in length. That is the reciprocal of strain, and thereby giving us the Young's modulus of elasticity to be load times length divided by cross-sectional area times the change in length. Making change in length the subject, we are going to get this change in length is equals load times the original length divided by cross-sectional area times the Young's modulus of elasticity. But load over area is what? It is stress. Now, the cross-sectional area of the steel rod will be given by pi over 4d squared. So this is going to be pi over 4 times. The diameter of the steel rod is 50 millimeters. We need to convert it to meters. That is going to give us 0.05 squared. It is going to give us an area of 1.9635 times 10 raised to the power of negative 3 square meters. So this is the cross-sectional area of this solid steel rod. Now from there, we can now determine the changing length in this steel rod, and we are going to say that the changing length will be given by the load applied on this section, which is 100 kilonewtons. We convert to newtons, so that is going to be 100 times 1000. Since 1 kilonewton is equivalent to 1000 newtons, then we multiply by the length of the steel rod, which is 2.5 meters. So times 2.5 meters, divide this by cross-sectional area of this steel rod, that is 1.9635. 1.9635 times 10 raised to the power of negative 3 times the Young's modulus of elasticity of steel, which is 200 giganewtons per square meter. So times 200 times 10 raised to the power of 9, converting it to newtons per square meter. Remember, 1 giganewton is equivalent to 1 billion newtons, and a billion 9 zeros. So when we do that, we are going to get the change in length of this steel rod to be 6.366 times 10 raised to the power of -4 meters. So that is the change in length. When we convert it to millimeters, we multiply it by 1,000. We are going to get a change in length of this steel rod to be 0.366 millimeters. So that is the changing length of this steel rod. Now we are told that when we bore this steel rod centrally, and then we subject it to the same rod of 100 kilonewtons, the elongation or extension will increase by 15%. Therefore, we are going to determine the increase in that extension. So this is 100%, an increase of 15% is 115%. So we are going to have 115% of 0.6366 millimeters, and that is going to give us a changing length of 0.732 millimeters. Awesome. Now from there, we are going to determine the cross-sectional area of this remaining part after we have removed or after we have bored this steel with a hole whose diameter is 25 millimeters. So we are going to determine the remaining cross-sectional area. Now, after we have bored this steel rod, we are going to determine its elongation, that is the elongation of the reduced section. And in this case, the elongation of this reduced section will be the elongation of this remaining solid part that has not been bored, which is going to be 2.5 minus x plus the elongation of this section that has been bored. So in this case, we are going to have this. The changing length will be given by stress times the length of the steel rod divided by the Young's modulus of elasticity. This one we are getting it from where? From here. We have said that changing length is rod times length divided by area times Young's modulus of elasticity. But this rod over area is stress. So we can have another formula that looks like this: stress times length divided by the Young's modulus of elasticity is equals to changing length. So that's what we are applying here. So this is the stress of the solid rod times the length of the solid rod divided by the Young's modulus of elasticity of steel. We are going to add that to the extension of this bored section or reduced section. So the stress of the reduced section times the length of the reduced section divided by the Young's modulus of elasticity of steel. Now, we are going to determine the stress of the reduced section, and we know that stress is given by load divided by the cross-sectional area. Therefore, the cross-sectional area of the reduced section, the cross-section that is going to remain, is going to be given by pi over 4 into d squared minus d squared. Why that? Because the total diameter here is capital D, and then we subtract this small diameter here. We are going to remain with the diameter of the shaded region, and therefore the cross-sectional area is now going to be pi over 4 into the diameter of the solid section is 50 millimeters or 0.05 meters, that is squared. We subtract the diameter of the bow or the hole is 25 millimeters. When you convert that to meters, that is going to be 0.025 squared. And that's going to give us a cross-sectional area of the shaded region being equal to 1.4726 times 10 raised to the power of -3 square meters. So that is the cross-sectional area. So we can now be able to get the stress of the reduced section. So the stress will be given by load 100 kilonewtons. We convert that to newtons, multiply it by 1000, divide this by the cross-sectional area, which we have gotten is 1.4726 times 10 raised to the power of -3 square meters. And when we do so, we are going to get the stress of the reduced section being equal to 67.9 times 10 raised to the power of 6 newtons per square meter. So that is the stress of the reduced section. Very good. Now from there, the stress of the solid rod will be given by load divided by cross-sectional area, which in this case is a load of 100 kilonewtons, convert it to newtons, divided by the cross-sectional area of the solid steel rod, 1.9635 times 10 raised to the power of -3. So the stress of the solid rod will happen to be 50.93 times 10 raised to the power of 6 newtons per square meter. So that is the stress of the solid rod. Good. Now, therefore, the elongation of the reduced section, that is this x, or the total elongation of this rod, we are going to have this. The change in length will be given by the stress of the solid rod multiplied by the length of the solid rod, which is 2.5 minus x, this solid section. So that will be the length 2.5 minus x. Divide this by the Young's modulus of elasticity of steel, that is E. Then we add that to elongation of this reduced section, which in this case will be the stress of the reduced section multiplied by the length to be bored, that is x. We still don't know how long we are going to bore it, divided by Young's modulus of elasticity of steel. So let's substitute everything in this formula. So in this case, we are going to have the stress of the steel of the solid rod is this one, 50.93 times 10 raised to the power of 6 newtons per square meter into 2.5 minus x. Divide this by the Young's modulus of elasticity of steel. That is 200 times 10 raised to the power of 9. Plus stress in the reduced section, that is 67.9. So 67.9 times 10 raised to the power of 6 times x, divided by the Young's modulus of elasticity of steel, 200 times 10 raised to the power of 6 is equals to the elongation that was increased by 15%, which is 0.732 millimeters, and in meters is going to be 7.32 times 10 raised to the power of -4. So that is what we are going to have. Now we are going to remove this 200 times 10 raised to the power of 9 by multiplying every section by that. So when we do that, we are going to have 50.93 times 10 raised to the power of 6 into 2.5 minus x. Remember this, when we multiply here or this part by 200 times 10 raised to power 9, they are going to cancel out. The same case to this section. So this one will be multiplied by 7.32 times 10 raised to the power of -4. Then we add 67.9 times 10 raised to the power of 6 times x is equals to 7.32 times 10 raised to the power of -4 times 200 times 10 raised to the power of 9. This one is raised to the power of 9 giganewton per square meter. Then we are going to divide through by 50.93 times 10 raised to the power of 6. So when we divide, we are going to have this divide by 50.93 times 10 raised to the power of 6. Divide this as well by 50.93 times 10 raised to the power of 6. This one the same case, divide it by 50.93 times 10 raised to the power of 6. When you do so, here we are going, the 2 will cancel out, so we are going to remain with 2.5 minus x plus 67.9 divided by 50.93. The 2 are going to cancel out. We are going to have it as 1.333x is equals to, when we divide the numerator with this denominator, we are going to have 2.8745. Then from there, take 2.5 this side of the equal sign, minus x plus 1.333x, that is 0.333x, being equal to 2.8745 minus 2.5, this 2.5 here. So this is going to give us 0.333x being equal to 2.8745 minus 2.5, that happens to be 0.3745. To get the value of x, divide both sides by 0.333. Divide this side as well by 0.333. And in that case, when we do so, we are going to get the value of x being equal to 1.12 meters. So that is the depth up to which we are going to make our hole. So we are going to go up to 1.12 meters. So ladies and gentlemen, that's how we go about it. Thank you very much for your support. Keep subscribing if you haven't yet subscribed, and we are going to be very, very grateful. Let's meet yet